Good morning, everyone. My name is Matt Allen, and I will be your moderator for today's webinar. I've been an account manager here at Flexpipe for the past 11 years, managing a wide range of accounts within the Canadian market, from junior oil and gas companies to major producers. We appreciate you joining today's webinar, From Lab to Field, how Flexpipe enables reliable CO₂ transportation, which will be presented by Dr. Hadi Narazapur. Hadi is a research and development engineer here at Flexpipe, specializing in reinforced thermoplastic pipelines for energy and CO₂ transportation. He holds a PhD in mechanical engineering from the University of Alberta and has extensive experience in composite materials, gas permeation, and structural integrity assessment. His work focuses on developing and testing advanced thermoplastic composite systems, combining experimental research with numerical modeling to enhance pipeline performance and durability. So today we encourage you to actively participate in the webinar. Please use the Q&A panel to ask questions, share your thoughts, and engage with our speakers. Any questions will be addressed at the end of the webinar during the Q&A section. Please note that this webinar is being recorded and will be available to watch after the webinar concludes. So without further ado, I'll hand it over to Hadi. The floor is yours.
Hello, everyone. Let me walk you through what we will cover today. First, I'll provide a brief overview of Flexpipe, introducing its core features and capabilities. Next, we will explore how Flexpipe products are applied in different phases of CO₂, highlighting their versatility and performance across various operating conditions. We will then dive into CO₂ permeation testing, discussing our methodologies and review the permeation rates at different phases of CO₂. After that, I'll share some real-world case studies to illustrate Flexpipe's track record in CO₂ transport. Finally, we will wrap up with a summary of key takeaways and we'll open the floor for your questions. This slide compares our main commercial available products, Flexpipe HT, rated for maximum operating temperature of 82 C, Flexpipe and FlexCord, which are rated for maximum operating temperature of 60 degrees C. The product envelope is currently being expanded to go to even higher temperature ranges, which I won't be discussing it today. Reinforced thermoplastic pipe, or RTPs, consists of three primary components. The thermoplastic liner. The liner serves as the innermost layer, providing a smooth, chemically resistant barrier that is in direct contact with the conveyed fluid, whether it's going to be gas, liquid, or emulsion. In Flexpipe HT, we use PERT, or polyethylene raised temperature, for the liner because it offers a higher maximum operating temperature. In Flexpipe and FlexCord product, we use high density polyethylene, or HDPE, for this layer. The next element is the load-bearing reinforcement layer, which delivers the pipe's mechanical strength. Flexpipe utilizes either unbounded glass fiber or high-strength steel cord to withstand internal pressure and external loads. The outermost layer is the protective thermoplastic cover, which shields the reinforcement from environmental factors and mechanical damages, ensuring the long-term durability and performance of the RTP. This table highlights the differences in nominal diameter, reinforcement material, operating temperature, which ranges from -29 C up to 82 degrees C, the maximum pressure rating from 750 psi to 2250 psi. The rear length for each product varies from 350 meters up to 2000 meters, depending on the pipe diameter. Pipelines are central to achieve net zero carbon emission by transporting captured CO₂ from sources to its storage facilities or its end users. However, there are challenges like material corrosion due to impurities in CO₂ and pressure fluctuations, which limits the use of conventional metallic pipes. Reinforced thermoplastic pipes, like Flexpipe, offer corrosion resistance and flexible installation methods, which can reduce the project and life cycle cost by up to 30% for typical gas application. The use of RTP pipes are also coming with its own challenges, as CO₂ dissolves in polymer liners and weaken the material strengths. The dissolved CO₂ permeates through the liner, which leads to annulus pressure buildup, um, increasing the delamination and failure risks. Impurities and chemicals also results in degradation and swelling of the liner or other polymeric components. That's why it's crucial to understand the permeation rates of CO₂ in its different phases when using RTPs for CO₂ transport applications. Also, it is essential to evaluate the resistance of the polymer materials used in RTP structure to ensure they can withstand the rapid gas depressurization events. Our products undergo rigorous testing, including pressure hold at elevated temperatures going up to 120 degrees C, chemical exposure, permeation and rapid gas depressurization, pressure cycling, bend testing, cold temperature impact, tensile compression, and pressure and thermal expansion tests. These testings ensure Flexpipe's reliability and performance in demanding CO₂ transport applications. Flexpipe has a strong history in CO₂ service with our first project in Alberta, Canada in 2009. Since then, we have installed over 250 kilometers across 20 projects at 8 locations in various CO₂ phases, but majority has been for gas phase CO₂ applications. Both Flexpipe and FlexCore products are used in various CO₂ phases, including gas, liquid, and dense phase. This plot shows the phase diagram of the pure CO₂ and breakdown of the installed pipe for each phases. Just a reminder, the critical point of CO₂ is at 7.39 MPa and 31.1 degrees C. The CO₂ phase that the RTP encounters depends on the transport's operating temperature and pressure relative to this CO₂ critical point. Flexpipe most installations are in the gas phase with more than 200 kilometers, but we have also completed projects in liquid and dense phases. With the first liquid phase installed goes back to 2016 with the total installation length of 10 kilometers. And the first project at dense phase was installed in 2012, and since then the total installation length is more than 45 kilometers. In order to provide the best guidance for our application engineering team and the end users, we performed the permeation testing at different levels, including pipe, liner, and film configuration. The results of permeation properties at each level will be cross-validated before implementing them to our permeation models. This ensures our permeation models are robust and reliable. The permeation tests are followed by rapid gas depressurization tests according to API 15S 3rd edition standard. This allows to evaluate the material resistance to pressure fluctuations after exposure and saturation of gases. We conduct permeation tests using different gases, such as CO₂, CH4, H2S, in presence of aromatics, water, and mixture of these components. Pictures on the right shows the testing equipment and setup for full pipe configuration for 3-inch to 6-inch size, the flat film cell, and our liner testing equipment, which is our tubular configuration, at 1-inch, 3-inch, and 6-inch sizes. In today's presentation, we only focus on the CO₂ permeation testing and its results. We implement 2 different approaches for permeation testing. In the first approach, permeation is measured using the time lag method, which tracks a cumulative mass per unit area over time at the downstream site. This method requires a closed volume at downstream to track increases in downstream pressure. The permeability coefficient can be determined from the slope observed at the quasi-steady state, as shown in this plot. The diffusion coefficient is then calculated using the intercepts between the tangent line at quasi-steady state and the horizontal time axis. In the second approach, the gas chromatography, or GC, is used to detect and measure individual gas components in multi-gas conditions. This model considers the maximum volume flow rate, sample thickness, surface area, and partial pressure gradient, providing a comprehensive understanding of a gas transport through polymers, which is used in more complex systems with multiple gas components. In either of methods, the permeability coefficient and diffusivity coefficient will be measured directly from the experimental results. On this slide, I'm showcasing the outputs from each testing method after completion. On the plot to the left, the yellow line illustrates the increase in downstream pressure following the initial breakthrough. The breakthrough time varies depending on temperature, polymer type, and the specific gas used. Throughout the experiment, we ensure that both the upstream pressure and the cell temperature remain stable. On the plot to the right, you can see the CO₂ gas component trace obtained using the GC measurement. The black line represents the CO₂ flux over time, and it highlights how the permeated flux responds sensitively to fluctuations in both pressure and temperature. Understanding the permeation properties of the liner in reinforced thermoplastic pipe is essential for determining the suitability of RTP for its intended application. To assess how phase change in CO₂ affect permeation, we examined different operating temperatures and pressures, which are represented here by dots in the schematic phase diagram shown here. We use two grades of liner material in our Flexpipe products, like HDPE and PERT. The samples we tested were like flat film discs, and we compared extruded samples versus compression molded samples, whether they are air-cooled or quenched in water. And the crystallinity range for those films varied between 55% up to 64%. The temperature range, we looked at the range from 23 degrees C up to 82 degrees C, and the pressure range from 7.2 MPa up to 10.3 MPa. And since we're considering a single gas component, the closed volume approach is used here for its simplicity. The fugacity of pressure is the value required at a given temperature to make the properties of a non-ideal gas satisfy the equation for the ideal gas condition. The plot on the right shows the fugacity of pressure for pure CO₂, which is plotted against the pressure. And by increasing both temperature and pressure, the CO₂ gas deviates from the ideal gas condition. And the fugacity can be calculated using the various sources, such as NIST reference properties report, or through the relations provided in scientific publications. In this presentation, we showcase the use of Penn-Robinson equation of state, which is freely available method and implemented in an Excel sheet. As temperature decreases, the deviation from ideal gas behavior becomes more pronounced, as shown in this plot. And just note that at 23 degrees C, the transition of pure CO₂ from gas to liquid is about 891 psi. So any pressure above that, basically the CO₂ is no longer in gas phase. This table summarizes one of our previously published work that mostly focused on the permeation properties at the supercritical phase of CO₂. Here we are comparing the HDPE and PERT permeation properties at different temperatures, ranging from 40 degrees C up to 82 degrees C. And the pressure is at 10.3 MPa. That's why the CO₂ is in its supercritical phase between those temperature ranges. The CO₂ transport properties measured using the time lag method here, and we accounted for fugacity and carefully controlled the sample preparation to ensure the reliability of the data. Just a reminder that the HDPE polymer is rated for maximum 60 degrees C operating temperature, and PERT is rated for up to 82 degrees C in our Flexpipe products. The results show that at lower temperature ranges, for example, 40 degrees C, the HDPE permeation rate is slightly lower compared to PERT. And at 82 degrees C, both polymers showed similar permeation rates. This slide shows the expanded work to cover wider range of temperatures and captures the phase change and the effect of increasing temperature investigated while keeping the pressure constant at 1500 psi or 10.3 MPa. Effect of different manufacturing method of films are also compared here. Results for compression molded samples are shown using the circle symbols, and squares are for the extruded films. The effect of fugacity is shown by comparing the fugacity adjusted curve, which is in blue, to the orange colored data, which we don't account for the fugacity of pressure. It highlights the underestimation of permeation rates if the fugacity of pressure is not considered while reporting the properties. The green squares shows the permeation coefficients when CO₂ is at its dense phase condition. The rectangle box shows here is the typical range of temperature in which the CO₂ transport lines operate. And as we see, the maximum operate temperature most of the time falls below 60 degrees C. This slide explores how temperature affects CO₂ permeation at lower pressure of 6.2 MPa, in which the CO₂ is going to remain in a gas phase condition. Plot on the left compares the permeability and diffusivity coefficients, and we observe the role of temperature in permeation and diffusivity coefficients follows the exponential growth. The plot on the right is showcasing the solubility coefficient variation versus temperature, and we noticed that the variation in solubility is less sensitive to the temperature. Here we are comparing the CO₂ permeation at two pressure range of 10.3 MPa and 6.2 MPa. Plot shows the permeation coefficient versus temperature, and the light blue color shows the gas phase, which is at lower pressure, and the dark blue shows the supercritical phase, which is related to 10.3 MPa pressure. Both are adjusted to account for fugacity of pressure to present the permeation coefficient. At higher temperatures, after accounting for fugacity of pressure, the permeation rates are very close to each other, and at lower temperatures, below the critical point, the permeation rate depends on the operating pressure, as the rates are higher for gas phase compared to the dense phase condition. This slide demonstrates how phase change between gas and supercritical phase impact the permeation properties. We looked at two temperatures of 60 C and 82 C. The phase transition occurs due to the change in pressure while the temperature remains constant. And the fugacity of pressure, the results are shown for both cases that fugacity is accounted or not. The variation in permeation coefficient and diffusivity and solubility found to be insignificant by this variation in the temperature and the phase change. At temperatures below the critical point of CO₂, which is around 31 degrees C, Change in temperature results in different phase change scenario. Here we investigated at 23 degrees C as pressure increases from 5.2 MPa to 10.3 MPa. We observe a phase change from gas to dense phase. And as a result, the permeation rate decreases by about 60%. We notice the diffusivity increased by 70% and solubility decreased by 70%. These findings highlight the importance of understanding the permeation through RTP at a different phase due to the dramatic change in permeation values and properties. This slide just summarizes the effect of CO₂ phase change at fixed temperatures. The top row shows when we have a phase change at a constant temperature of 60 C and 82 C. And the bottom row is for the 23 degrees C. Under constant temperature condition, pressure fluctuations that results in a phase change between the gas and supercritical phase does not affect the permeation rates. While operating at a lower temperature, specifically below the critical point of CO₂, the pressure fluctuation results in a phase change between gas to dense phase. And we noticed that the permeation rates at dense phase are about 60% lower compared to the gas phase. And this relative reduction may differ at other temperature, which needs to be investigated for each cases. Here I also wanted to touch base on the RGD or rapid gas decompression test and resistance of our RTPs. The resistance of both polymer components and pipes to rapid gas depressurizations of the line is crucial for any CO₂ application. And images on the top shows here the cross-section of the FlexCord pipe after rapid gas depressurization and highlighting no signs of blistering or delamination. Images in the middle row shows the SEM results of the HDPE liner after 20 RGD cycle of CO₂ exposure at the supercritical phase, which is the most aggressive one. And images at the bottom shows our typical flat film samples after the permeation and RGD tests. Let's take a look at the real-world case study involving a tertiary recovery system that uses high concentration of CO₂. The first CO₂ gathering and transfer lines for this project were installed in 2012 using the Flexpipe, operating at a typical pressure of 300 psi, and 55 kilometers have been installed for low pressure and high concentration application. And operating temperature ranged from 5 degrees C up to 44 degrees C for that. Starting in 2013, Flexport was introduced for high pressure CO₂ injection line with a total length of 30 kilometers installed for that project. And these lines handle concentration up to 100% CO₂ at pressures as high as 1500 psi. And the temperature ranges of operation was between 6 degrees C up to 55 degrees C. Altogether, this project spans 85 kilometers, and remarkably, there have been 0 incidents or accidental release throughout its operation. This case highlights the reliability and safety of Flexpipe and Flexport solutions in demanding CO₂ transport environment. To summarize our findings, we experimentally investigated CO₂ permeation properties through PERT and HDPE material under various phase conditions, including compressed liquid, gas, and supercritical states using the closed volume permeation approach. They reported how changes in temperature and pressure affect permeation rate, diffusivity, and solubility for common CO₂ transport applications. Importantly, we showcased that neglecting the effect of fugacity of pressure in the gas and supercritical phase leads to a significant underestimation of the permeation rates. And these findings highlight the importance of understanding the permeation through reinforced thermoplastic pipes at different phases, as permeation values can change significantly depending on the operating condition and the pressure fluctuations. Finally, both HDPE and PERT material used in Flexpipe and FlexCord have demonstrated resistance to rapid gas depressurizations at their respective maximum operating pressure and temperature that ensures the reliability and safety in CO₂ transport applications. I would also like to acknowledge the support from University of Toronto and Innotech Alberta in Edmonton for performing the permeation test. And this research was funded by Flexpipe and NSER Canada. And a special thanks to those involved in technical discussions for this work. And now the floor is open for any questions.
All right, well, thank you all for joining us to learn about Flexpipe's material performance and CO₂ applications. As Heidi just mentioned, we'll now begin the Q&A session. Just a reminder, please submit your questions using the Q&A panel within the webinar platform. We'll kick off the first question. How is the integrity of reinforcement and end fittings assessed for CO₂ applications?
In the entire pipe structures, we do the integrity assessment through the full pipe pressurization. So that covers the reinforcement, end fittings, O-rings, and all the components used in the actual field. And yeah, mostly it's through the pipe permeation testing, and then followed by RGD, which is based on the API 15S standard.
Okay, great. Second question. Have you looked into the same/similar testing with FlexCord?
Yes, in terms of pipe level testing, basically both Flexpipe and FlexCords follow the same. Basically, they have to go through the same testing procedure in terms of the saturation and then permeation and then RGD. In terms of component material like liner material and O-rings, again, they follow the same approach, which is basically just a difference in terms of the maximum operating temperature, which is different from Flexpipe HT and Flexpipe and FlexCord.
Okay, great. Moving on, what methods used assess polymer integrity after rapid gas decompression?
We do, as I shown here, we do basically look at the optical micrograph and SEM and look for any slitting or blistering sign. We also measure the density of the polymer before and after each RGD test to make sure that we don't see any significant change, which shows the polymer degradation if there is a significant change in the density measurement.
Okay, continuing on, how is the solubility coefficient measured for different phases?
In this work, we calculated the solubility based on the experimentally measured diffusivity and permeability coefficients through the formula that correlates these parameters together. Yes, and we didn't measure the solubility independently, so it was a outcome and results of the measured diffusivity and permeability coefficient, basically.
Okay. What is the error in the permeation measurements and results?
For the data I showed here, they're all triplicates. So for each condition, we repeat a test for 3 times. On the average, a standard deviation is below 5%. But for some cases, we had a maximum standard deviation to about 10%.
If there are no more questions, again, we would like to thank you all for joining us, and that will conclude today's webinar.